So next what we're going to do is we're going to use matrix notation to express this type of linear function that we see up top using less writing. So the complete information we need to reconstruct this linear function is completely encoded basically by this matrix that has all the numbers that go in front of the variables, like so. And it's also encoded by this column vector that keeps track of these four constants that are at the right hand side. So what we're going to do is we're going to talk about some operations that we do to matrices, some things we can do with matrices that make writing these types of functions much cleaner. So the first operation is called matrix addition. If we have two matrices that are of the exact same size, same number of rows, and same number of columns, we can add them together. And this addition works the same way as it does for vectors. We just go through entry by entry and we add up the two entries that are in the same position and we write down the number that we get. So for example, we've got these two matrices here. If we add 1 and minus 1, we get 0. If we add 0 and 7, we get 7. If we add 3 and minus 2, we get 1. And if we add 4 and 5, we get 9. So matrix addition is just like vector addition. It doesn't take a lot of extra brain power, although it does take a lot more time. And we've seen this before for vectors. That's the first operation that we're going to need. And matrix addition acts mostly the way that you'd expect normal addition to act most of the time. Matrix multiplication is something new, and we're going to need to spend some time practicing it to make sure that we get it right. So it's extremely convenient for encoding linear functions, but it takes a little work. The first thing we need is we need two matrices, A and B, and we have to have a matchup between their sizes. We have to have a matrix A and a matrix B where the number of rows of the first matrix is the same as, the number of rows of the second matrix is equal to the number of columns of the first matrix. If that's true, then they have a product. So in one way you can think of it is that if we have an n by m matrix and an m by p matrix, we're allowed to multiply them. The middle sizes cancel off and we're left with an n by p matrix. We just have no rule for multiplying them if they're not matching sizes like this. When we multiply them, to find all the entries in the output, we go through step by step and we keep taking dot products. We take the dot product of each row of A with each column of B and then put the results into a square grid. And with all of these things, the important rule to remember is rows and then columns. An n by m matrix means it's n rows and m columns. The matrix multiplication rule multiplies the row of the first matrix with the column of the second matrix. Always rows and then columns. So, as an example, if we want to multiply these two matrices together, the one on the left is 2 by 2 and the one on the right is 2 by 2, those inner sizes cancel off and we're going to be left with a 2 by 2 matrix as the output. And to figure out, for example, the entry in row 2 and column 2, we go through and we take the dot product of row 2 of the source and row 2 of the target. We take 3 times 6 plus 4 times minus 1, and that gives us 14. Similarly, if we wanted to know the entry in row 2 and column 1, we would go through and we would take the dot product of the second row with the first column, and that would be 3 times 5 plus 4 times minus 2, which is 15 minus 8, that's 7. And so it's just a sequence of dot products. It may be a lot of them depending on the size of the matrix, but they're all operations that we know how to do. We have to just learn how to remember how we do them when we're doing matrix multiplication. Always row of the first one times a column of the second one. Now, there's a special type of matrix that's very, very common and shows up with these operations. It's called an identity matrix. An identity matrix is a special matrix that has a 1 or a sequence of 1s on the diagonal that goes from upper left to lower right, and it has zeros everywhere else, and it has to be square. We usually write I for it with the understanding that we should know exactly what size it is. And identity matrices have the special property that when you multiply by them, it doesn't do anything. The identity times anything on the left is equal to what you ended up with, and the identity times anything on the right is whatever you left off with. But you have to have the understanding that the sizes have to match up in order to do the multiplication in the first place.